Every modern diffusion model is trained to denoise. You take a clean image, add noise, and ask a neural network to undo the corruption. But here is something strange. Almost none of these models actually predict the clean image. Instead, they predict the noise that was added. For years, this has been the default, and it works well enough that nobody questioned it. But what if this choice, predicting noise instead of the image, is not just a minor design detail, but a fundamental mistake that gets worse as your images get larger? To understand the problem, we need to see how diffusion models frame the denoising task. Given a clean image X and random noise epsilon, we create a noisy version ZT by blending them together. ZT equals T times X plus 1 minus T times epsilon. The network sees ZT and must recover something useful. There are three natural targets it could predict. First, X prediction. Output the clean image directly. Second, epsilon prediction. Output the noise component. Third, V prediction. Output the velocity, which is simply X minus epsilon. Here's the key insight that made people think this choice does not matter. These three quantities are algebraically linked. If you know any one of them, you can compute the other two from the blending equation. So the network can predict whichever is most convenient, and you recover everything else for free. This algebraic equivalence led to a widespread assumption. The prediction target is just a matter of loss weighting. Pick epsilon, pick V, pick X. It should not matter because the information content is the same. And for small images, this assumption holds up perfectly. But the authors of this paper discovered something striking. As images get larger and patch dimensions grow, this equivalence completely falls apart. Let's look at exactly how badly it breaks. The authors ran a clean experiment on ImageNet at 2 resolutions, using the same transformer architecture with different patch sizes. The results are dramatic. At 256 by 256 resolution with 16 by 16 patches, each patch becomes a 768-dimensional vector. With X prediction, the model achieves an FID around 8.6, which is a perfectly reasonable score. But switch to epsilon prediction, same model, same training, same everything else, and the FID explodes to 372. That is not a small degradation. That is a catastrophic failure. The generated images are essentially garbage. V prediction fares slightly better but still fails badly, landing around FID 96. And this is not a loss weighting issue. The authors tested all 9 combinations of prediction space and loss space. X prediction works with any loss. Epsilon and V prediction fail regardless of how you weight the loss. Here is the critical clue. At 64 by 64 resolution with 4 by 4 patches, each patch is only 48-dimensional. And at this lower dimensionality, all 9 combinations work fine. FID scores range from about 3, 5 to 6, 2, and there is no catastrophic failure for any prediction target. The failure is specific to high-dimensional patches. Something about predicting noise in high-dimensional space is fundamentally harder than predicting the clean image. So why does dimensionality matter so much? The answer comes from a classical idea in machine learning, the manifold hypothesis. The manifold hypothesis says that natural data, like images of real objects, does not actually fill the full space of all possible pixel values. Instead, it lives on a much lower dimensional surface, a manifold, embedded within that high-dimensional space. Think of it this way. A 16 by 16 color patch has 768 pixel values, so it lives in a 768-dimensional space. But the set of patches that look like natural image content, textures of fur, edges of buildings, patches of sky, those occupy a tiny curved surface within that vast space. Most random 768-dimensional vectors look like static, not like anything from the real world. So the intrinsic dimensionality of natural image patches is much lower than 768. Maybe it is on the order of tens or low hundreds of dimensions, not hundreds or thousands. Now here is where the prediction target matters. When you ask a network to predict the clean image X, its ideal output lives on this low-dimensional manifold. Even a network with limited capacity can learn to project onto this manifold because the target has low intrinsic complexity. But when you ask it to predict noise epsilon, the target is a random vector that genuinely fills all 768 dimensions. There is no manifold structure to exploit. The network needs capacity proportional to the full dimensionality of the observation space, not just the data manifold. And velocity v equals x minus epsilon inherits the same problem, because subtracting a low-dimensional signal from a high-dimensional one still gives you a high-dimensional target. The authors validate this theory with an elegant toy experiment. They take two-dimensional data and embed it into progressively higher dimensional spaces using fixed random projection matrices. Then they train a small 5-layer network to generate samples using each prediction target. At 2 dimensions, everything works. At 16 dimensions, epsilon and v predictions start degrading. At 512 dimensions, they fail completely, producing only noise. But X prediction keeps working, even at 512 dimensions, because the network only needs to recover the 2-dimensional manifold, regardless of how high the embedding dimension is. So the core message is this: predicting clean data and predicting noise are fundamentally different tasks when data is low-dimensional, but the observation space is high-dimensional. Loss reweighting cannot fix this. It is a capacity issue baked into the geometry of the problem. If X prediction is the right approach, then the natural question is, how simple can we make the architecture? The authors take this idea to its logical extreme and build what they call just image transformers, or JIT. The design philosophy is radical simplicity. JIT is a plain vision transformer applied directly to raw pixel patches. No learned tokenizer, no variational autoencoder, no perceptual loss, no self-supervised pre-training. You take non-overlapping patches from the image, project each patch linearly into the model's hidden dimension, add positional embeddings, and run standard transformer blocks. Time and class conditioning use adaptive layer normalization, following the convention from diffusion transformers. The output layer projects each token back to patch dimensions. That is the entire architecture. The key insight is that with X prediction, you do not need the network's hidden dimension to match or exceed the patch dimension. JIT uses 768-dimensional hidden states to process patches that are 768-dimensional at 256 resolution, but scales to 3,072-dimensional patches at 512 resolution, and even 12,288-dimensional patches at 1,024 resolution, all with the same hidden size. There is one more surprising finding about the architecture. The authors tried adding a low-rank bottleneck to the patch embedding layer, compressing patches from their full dimensionality down to as few as 16 or 32 dimensions before expanding to the hidden size. Conventional wisdom says throwing away information should hurt, but it actually helps, improving FID by about 1.3 points. This makes perfect sense under the manifold hypothesis. If the real information in each patch is only tens of dimensions, then an explicit bottleneck encourages the network to learn that low-dimensional structure rather than wasting capacity on noise. So the theory is clean and the architecture is simple. But does it actually produce competitive results at scale? The authors scale JIT across multiple resolutions and model sizes on ImageNet, and the results are strong. One elegant property of JIT is that it maintains a fixed sequence length of 256 tokens across resolutions by proportionally scaling the patch size. At 256 by 256, patches are 16 by 16 pixels. At 512 by 512, patches are 32 by 32. At 1024 by 1024, patches are 64 by 64. This means computational cost stays roughly constant regardless of resolution. With the base model, JITB, the FID scores are 4 at 256 resolution, 6 at 512, and 8 at 1024, all with similar parameter counts around 130 million and similar compute around 25 to 30 gigaflops. Scaling up model size brings substantial gains. At 256 resolution with 600 training epochs, JITB achieves FID 3. 7, JITL reaches 2. 4, JITH gets to 1. 9, and JITG hits 1. 8. At 512 resolution, the largest model JITG achieves FID 1. 78, which is actually better than its 256 result. This is remarkable because larger patches mean higher dimensional patch vectors. Up to 3,072 dimensions for 32 by 32 patches, yet X prediction handles this gracefully. How does this compare to the broader field? Latent diffusion models like DI-T achieve FID around 2. 3 on ImageNet 256, but they depend on a separately trained variational autoencoder and operate in a compressed latent space. Methods like RAPA and DDT push below FID1, 5, but they require additional self-supervised pre-training stages like DINAV2. GI-T operates directly on pixels with no external components, making it a fundamentally simpler system. Among pixel space methods, GI-T is competitive with or better than prior approaches that required much heavier architectures like UNets with over 1,000 gigaflops of compute per sample. These results raise a bigger question. If X prediction is so much better in high dimensions, why has the field been building around noise prediction for so long? The authors argue that many design choices in modern diffusion architectures are, in retrospect, implicit workarounds for the limitations of noise prediction. Consider why UNets became the dominant architecture. Their dense convolutional structure with overcomplete channel representations, often outputting feature maps with 128 channels per spatial position, provides enormous capacity in high-dimensional pixel space. This extra capacity is exactly what noise prediction demands. Similarly, the trend towards smaller patch sizes and hierarchical processing in vision transformers can be seen as reducing the per-token dimensionality to a regime where noise prediction still works. And the entire latent diffusion paradigm, compressing images through a VAE before running diffusion, serves the same purpose, reducing dimensionality so that noise prediction does not hit the capacity wall. X prediction sidesteps all of these workarounds. That said, there are clear limitations. The manifold assumption is just that, an assumption. It holds well for natural images, but whether it extends to all data modalities is an open question. The authors also did not explore combining X prediction with self-supervised pre-training or auxiliary losses, which could potentially push results further. And there is a practical consideration. At very large patch sizes, like 64 by 64 for 1024 resolution, each patch contains over 12,000 pixel values, and the linear projection into the hidden space becomes a significant compression step. Whether this remains sufficient for truly high-fidelity generation at extreme resolutions is still untested. The message of this paper is deceptively simple. Diffusion models are meant to denoise, so let them predict the clean image, not the noise. In low dimensions, it does not matter. But as patch dimensions grow into the hundreds or thousands, the manifold hypothesis turns prediction target selection from an aesthetic choice into a make-or-break architectural decision. And by embracing X prediction fully, the authors show that you can strip away the tokenizers, the pre-training, the auxiliary losses, and the complex architectures, and still generate high-quality images with nothing more than a plain